Hey there, chemistry students. This is Ms. Ruhr. This is podcast 9.5. We're going to talk about titrations. Okay, so what in the world is a titration? Ms. Ruhr, you keep talking about this. What's going on with it? All right, well, a titration is a method that we use to perform a neutralization reaction. And of course, a neutralization reaction is between an acid and a base. And we use it to determine the concentration of an unknown acid or an unknown base. Okay. You use something called a titrant, which is your standard solution, and your titrant will go into your burette. Now the burette is this nice long thing right here. This is the burette, and the titrant goes into the burette. Okay, and then what you're testing will go into the flask. That would be called your analyte. Okay, so your titrant goes into the burette, and what you're testing, what you're analyzing, is called your analyte. Okay, now, if you go to college, you could work somewhere where you're working with a stir plate, and so you would have a stir bar inside, which is that little flea, and it actually stirs it for you. However, we don't have those here, so here you will be stirring your flask as you work. Now, that's why we use a conical flask, such as an Erlenmeyer flask. Okay, and you've dealt with these before, so we use an Erlenmeyer flask because when we swirl them, it will keep your solution inside of the flask. It won't allow it to come up and out through the sides. Okay, here where it says the tap, there's a thing, there's a little knob there that you can turn. Okay, we call that the stopcock. And the stopcock is what we're used to turn and allow some of the titrant to come out or to not come out. You can turn it so that it comes out quickly, or you can turn it so that it drips out extremely slowly. That is completely up to you, but you want to make sure that you don't go past your endpoint. Okay, so let's talk about more of this. We have something called, well, let me change my color. Okay, we have something called an equivalence point. And our equivalence point is where the amount of hydrogen ions or hydronium ions is equal to the amount of hydroxide ions. That is what we call neutralized. That's where it is completely neutralized. Now, neutralized doesn't necessarily mean that it's a pH of 7. Okay, it just means that there's equal amounts of those two ions. So our equivalence point could be higher than a pH of 7, it could be lower than a pH 7, or it could be at a pH of 7, depending on what you are mixing together. Okay, and then we have something called the endpoint. And the endpoint is where your indicator will completely change color. Okay, and we'll talk about these indicators in just a minute, but you use an indicator to be able to tell when the reaction has reached its equivalence point and then when it has gone past. And we perform these using what we call a standard solution. And a standard solution is a solution that contains a precisely known concentration. And we say it's a precisely known concentration because it has to be exact. Okay? Usually this is going to be something that is bought, and it's bought directly from the company, or it could be something that you make and then you do a titration to standardize it. Okay? And what you do when you standardize it is you are excuse me, you're doing titrations and then back checking to make sure that your calculations, by calculating that your concentration is what you know it to be. Okay, and we would use these to determine the unknown concentration of an acid or base. All right, so indicators. Indicators, these are compounds whose colors are sensitive to pH. Okay, so they change based on pH. They're either going to be weak acids or they're going to be weak bases. Okay, and they're usually called what we call buffers. Okay, and there is called as a position called a transition interval, and that's the pH range over the indicator changes color. Okay, now you can use a multitude of different indicators, and these are just some of them. The one that we will use the most in the class, the one that we will use is phenolphthalein, and phenolphthalein is more of a universal type. I don't want to say it's a universal indicator because it's not, but it's one that's used most commonly because most of the pH changes that we're going to do will occur between 8 and 10. Okay, now, it would make more sense to use bromothymol blue, because we want to do those pH changes that happen at the neutral point. The problem is that it doesn't always work, so we will use something called phenolphthalein. If you put phenolphthalein into an acid, it is a colorless liquid, which means it looks like water. It's colorless. And then when you make it more basic, it becomes pink. It's a nice, pretty pink. If you get that nice, pretty pink, you've gone too far. If you've got it colorless, you haven't gone far enough. Or vice versa, depending on what you're starting with. You want to get something that's right in between. So you want an extremely faint pink to show up. And if it's extremely faint pink and you can compare it to a piece of white paper and you can see that pink, that's where you want to stop. If you go all the way to pink, you've gone too far. Okay, so titrations, yes, they will test your patience. All right, so let's talk about titrations. When we do a titration, and I will show you a titration in class, I'll demonstrate it for you, and you will do plenty. Okay, but when we do a titration with a strong acid with a strong base, our equivalence point, remember that's where our OH is equal to our H3O plus. Our equivalence point will be here. I need a different color. Our equivalence point will be here at a pH of 7. Okay, that's our equivalence point. I think I need a different color, a little bit darker. Okay, so the equivalence point where our hydronium ions and our hydroxide ions are equal. That would be at a pH of 7. And the reason for that is because they both completely dissociate. Okay. Now, what happens if we do a weak acid with a strong base? Well, if we do a weak acid, oh, and let me go back one more. Let's go back one more second. Okay, notice how strong acid because it has a lower pH, strong base because it has a higher pH. It doesn't matter if it's here or it's all the way at the top. It's still a strong base, and it doesn't matter if it's here or all the way at the bottom. It's still a strong acid. What you're identifying it as a strong acid and a strong base is where that equivalence point is at 7. Okay, so with a weak acid and a strong base, the weak acid, the pH is a little bit higher. Your strong base, you still have a high strong base, or high pH. Your equivalence point, because it's a weak acid with a strong base, is going to be slightly basic. So our equivalence point is going to be above 7. Okay, our equivalence point. Remember, our equivalence point is where the hydronium ions are equal to the hydroxide ions. Right? So above 7. You need to know this. You might want to make sure you memorize this. All right. Actually, this is 7 here, isn't it? Yeah, Miss Ruark, you should pay attention to your diagrams. I'm sorry. Okay, so this is where our equivalence point is. 7 is actually going to be around here somewhere. So that would be our pH of 7. Okay, what if we had a strong base with a strong acid? Well, it's the same thing as a strong acid with a strong base. They're both going to completely dissociate. They're both going to completely break down and form water and a base, or water and a salt, and so our equivalence point will be at 7. Okay, and then on the last one, we have a weak base with a strong acid. Okay, well, our pH of 7 should be here in the middle, right? So if we have a weak base with a strong acid, the strong acid is going to be a little stronger than the base. So our equivalence point is going to be lower than 7. And notice how we start off with a lower, it's not an extremely high pH, but it's still greater than 7. And we end with a very low pH, which gives us a very strong acid. Okay, and that's about it, guys. So I will see you in class so we can go through all this junk later. Okay, all right, see you then.